Hello guys, this is Celso. In this second tutorial video about the transformer element, we will focus on how to define this element in different connections in OpenDSS scripting language. Let's start with a simple single-phase two-winding transformer. As we saw in the last video, both the short-circuit impedance and the open-circuit admittance are modeled in the secondary side of the transformer. I will first assume that both sides of the transformer are grounded. Then, also assuming a three-phase system, the rated voltage of this element should be aligned to ground voltage. Let's consider that we are going to work in a three-phase system whose voltage levels are 115 kV and 4.16 kV. I will name our transformer as TR. It is a single-phase transformer with two windings, and I'm going to set some values here for its series reactance, its losses, and magnetizing current. The first winding is connected to bus A, and its rated voltage should be 115 kV divided by square root of 3, that is roughly 66.39 kV. Note that bus equal to A by default means that this winding is connected between node 1 of this bus and ground. Let's set a rated power of 100 kVA. The second winding is connected to bus B, and for a line-to-line voltage of 4.60 kV, the corresponding line-to-ground voltage is 2.4 kV. The voltage bases are 115 kV and 4.60 kV. Let OpenDSS define the voltage bases for each bus for us. After solving the system, we can check that the voltage levels are around of what we have specified. The small difference is due to the approximations we have done for the division by square root of 3. Another way of specifying the windings of a transformer is by using the parameters kVs, kVAs, and buses. In each of those parameters, we need to set two values, the first and the second one for the first and the second winding, respectively. As you can see, we get the same results. Now, assuming that the secondary side of this transformer is supposed to supply a line-to-line voltage, 4.16 kV. In this case, we can connect the secondary of the transformer to nodes 1 and 2 of bus B. In OpenDSS, we need to change the rated voltage of the secondary side of the transformer to 4.16 kV and also update the bus parameter definition to B.1.2. In order to have the same nodal voltages in magnitude at the secondary side of the transformer, I will define the connection of the secondary winding as delta and the connection of the first winding as Y. Solving the circuit, we can see that, in fact, the nodal voltages of bus B are equal in magnitude and the secondary line-to-line voltage level is 4.16 kV, as desired. If you want to use the shorter way of declaring a transformer, the connections can be specified through the parameters cons, like the following. Don't forget to adjust both bus B connection and voltage levels. Now, let's explore some three-phase transformers. There are two options to define a three-phase transformer. The first one consists in the connection of three single-phase transformers, and the second one consists in declaring a single three-phase transformer. For example, suppose that we would like to define a three-phase delta Y-grounded transformer by using the first method. Then we should define three single-phase transformers, which will be called as A, B, and C. The connection of the three-phase transformer will depend on how we connect these three single-phase transformers to bus A and B. In this case, as we want the primary side in delta, we can connect the upper node of a single-phase transformer to a lower node of a different single transformer, like the following. Then, each of these connections should be attached to distinct nodes of bus A. For a Y-grounded connection, we need to connect the lower nodes of each winding to ground, and the upper node to a different node of bus B. Let's understand what are the outcomes of this connection to the phase shift between primary and secondary. Let's call the nodal voltages of bus A as V1P, V2P, and V3P for nodes 1, 2, and 3, respectively. Assume that these voltages are symmetric. The voltage across the first winding of transformer A is V1P minus V3P. That will be called V13P, and that is equal to square roots of 3 times V1P with a phase shift of minus 30 degrees. Then, Assuming that the number of winding turns of each transformer is N1 for the primary and N2 for the secondary, we can say that the voltage across the secondary side of transformer A, V1S, is equal to N2 divided by N1 times V1 3P. Hence, we can say that there is a phase shift of minus 30 degrees between the secondary and the primary side of this three-phase transformer. Minus 30 degrees is equal to plus 330 degrees. That is 11 times 30, or pi divided by 6 radians. For this reason, this three-phase transformer is also called as dy minus 30 and dy 11. Back to OpenDSS, as the primary side of each single-phase transformer is connected between two phases, let's define their connection as delta, and y for the secondary. The voltage levels of the primary side should be 150 kV and the secondary should be 4.16 kV divided by square root of 3. That is roughly 2.4 kV. We don't want to use this other transformer here, and we need 3 single-phase transformers, so I'm going to copy and paste this guy here 2 times. The first one will be transformer A and the others will be B and C respectively. All we have to do now is to define the connection of each bus correctly. According to our drawing, the first winding of transformer A is connected to nodes 1 and 3 of bus A, and the secondary winding is connected between nodes 1 and ground of bus B. The first winding of transformer B is connected to nodes 2 and 1 of bus A, and so on. By solving the circuit and checking the nodal voltages, we can verify the phase shifts of minus 30 degrees between primary and secondary sides, as expected. We can declare the same transformer by using a single three-phase transformer. Let's call it as transformer ABC, and it has 3 phases. We can delete the nodes from the bus definition, because the connections delta and y for the primary and the secondary side take care of the bus connection for us. We need to update the rated voltage of the secondary side to the line-to-line voltage to 4.16 kV, and the rated power of the transformer must be multiplied by 3 in order to have the correct values for the series and shunt resistance and reactances calculated based on the parameters XHL, load loss, no load loss, and IMEG when they are converted to ohms internally in OpenDSS. To set the phase shift, we can use a parameter called lead lag. If we set it to lag, it means that the secondary side of the transformer will lag the primary by 30 degrees, as we can see by solving the circuit. Now, suppose that our transformer is a step-up transformer with a secondary rated voltage of 200 kV. Keeping everything else as the same and solving the circuit, we see a phase shift of plus 30 degrees instead of minus 30 degrees, even though we set the lead lag parameter to lag. Why is that? It is because there is actually no consensus of which side of a transformer is the primary side and the secondary side. In OpenDSS, the reference for the phase shift is the winding with the highest rated voltage. For this case, lead lag equal to lag means that the first winding will lag the second winding. Then, if we still want to keep a phase shift of minus 30 degrees for these voltage levels, we would need to set lead lag to lead, as one can see by solving the circuit with this modification. If you want to define a three-phase transformer delta Y grounded with 3 single-phase transformers and a phase shift of plus 30 degrees, all you need to do is change the connection of the first winding of each transformer. The first winding of transformer A should be connected between phases 1 and 2 of bus A, the first winding of transformer B between phases 2 and 3, and the first winding of transformer C between phases 3 and 1. The secondary side remains unchanged. In this case, the voltage across the first winding of transformer A becomes V12P, that is equal to square root of 3 times V1P with a phase shift of plus 30 degrees. Then, the phase shift between V1S and V1P is equal to plus 30 degrees. This transformer is also called as dy30 and dy1. In OpenDSS, by adjusting the connections to the buses A and B, we can see the phase shift of plus 30 degrees. And, by using a single three-phase transformer, all we need to do is to set the parameters lead lag to lead. From now and so on, we will define all three-phase transformers as a single three-phase transformer. Suppose that we want to define a three-phase transformer in a Y-grounded connection, like the following. In OpenDSS, all we have to do is to change the connection of the first winding to Y. Note that even if we leave the parameter lead lag, it doesn't affect the solution, as there is no phase shift for a Y-Y connection. If we want to define a three-phase transformer in a Y-grounded, Y-ungrounded connection, we need to clearly specify the connections of the second winding, including the fourth isolated node. It can be noticed that the fourth node appears in the voltage line neutral report. The voltage of this node is zero because there is nothing connected to the secondary side of this transformer. If we connect an unbalanced load, for example, a single-phase load connected to phase A, we can now see that the voltage of the fourth node becomes relevant. In fact, in this case, the load current is flowing entirely through the fourth node. It is also possible to use an impedance to ground the transformer. Suppose, for example, a three-phase transformer with its primary side in a Y-grounded connection and its secondary side in a Y-grounded through a reactor. In this case, all we have to do is to add a reactor between node 4 and ground in the secondary side. The reactor element can be used for this purpose. Let's set its name to ground. It is a single-phase element connected between node 4 of bus B and ground. And let's also set a hypothetical resistance and reactance of 10 ohms each. Now, as the system is grounded, we can ground a single-phase load. As you can see, the voltage of node 4 has significantly changed, as the load current flows entirely through this impedance. Finally, let's consider a split-phase transformer. In OpenDSS, this transformer is modeled as a three-winding transformer, in which the second and the third windings are connected to each other. Let's assume that the primary side is grounded. The upper node of the second winding and the lower node of the third winding are connected to phases 1 and 2 of bus B, and the lower node of the second winding and the upper node of the third winding are tied to each other and grounded. The voltage level of both the secondary and the tertiary winding are the same. Then, supposing a voltage V across each of those windings, the voltage between nodes 1 and 2 of bus B, V12, is equal to 2V, and the line to ground voltage of nodes 1 and 2 are equal to V in magnitude. The opposite polarity between these voltages are then responsible for the voltage 2V across nodes 1 and 2. Back to OpenDSS, let's define this transformer. It will be called simply as TR. It is a single-phase transformer with three windings. As it has three windings, we need to specify the reactances between the first and the second winding, XHL, the first and the third windings, XHT, and between the second and the third windings, XLT. I'm going to delete the load loss because now we have to specify the series resistance of each winding separately. We can also delete the lead lag parameter. The first winding is connected to node 1 of bus A and ground, so its rated voltage should be 66.39 kV. And let's set a rated power of 10 kVA. Let's assume that this transformer is supplying a 2.4 4.8 kV system. Then, the rated voltage of the second and the third windings should be 2.4 kV. Pay attention to the bus's specification. They are responsible for setting the polarity of each winding. After solving the circuit, we can check that the voltages at nodes 1 and 2 of bus B are opposed in phase, and the voltage between nodes 1 and 2 is around 4.8 kV. By adding a single-phase load to node 1, we can see that the voltage of nodes 1 and 2 become more asymmetric. Changing the load's rated voltage to 4.8 kV and the connection to nodes 1 and 2, the load current becomes evenly split between the second and the third windings, making the system more symmetric, as you can notice by the phase difference of 180 degrees between the nodal voltage of bus B and the voltage magnitude. Finally, observing the currents in elements report, one might be induced to think that the load current flows through ground. However, this is not the case. Both the secondary and the tertiary windings are connected to ground, but they are also connected to each other. Then, the same current flows through both windings, not through ground. The apparent misunderstanding is due to the fact that the currents flowing in each winding are reported separately from each other. In fact, there is no load connected to ground in this example.